Hi friends, my name is Saidaya. I'm from class CSCC. The topic that we are going to discuss is computer memory and arithmetic. A look under the hood. The topic that we are going to discuss is from the subject computer organization architecture. So introduction. We have many places in which to store your data. You might keep your identification and credit cards in your wallet, where you can get them quickly. However, space is limited, so you can't keep all your important information there. Instead, you might carry current papers for work or school in a backpack or briefcase and store old papers in your desk or file cabinet. Any papers you don't think you'll need but you are afraid of throwing out might be stored in an attic basement or storage locker. You can think of your wallet, backpack, desk, and attic as a hierarchy of storage spaces. The small ones give you faster access to data that you often need. The larger ones gives lower access but more space. For the same reason, computers also have the hierarchy of storage units. Memory management systems try to store information that you will soon need in a unit that gives fast access. This means that large vectors and arrays are broken up and moved piece by piece as needed. You can write a correct computer program without even knowing about memory management. But attention to memory management allows you to consistently write programs that don't have excessive memory delays. So some tools on the memory management that were given by John Hennick and David Pattinson. It was good. Detailed description of memory hierarchies. In MATLAB, the underlying matrix decomposition software is drawn from the LAPACK Fortran suite. It's based on a set of basic linear algebra subroutines, which are provided by hardware manufacturers to optimize operations such as inner product Saxby matrix multiplication, and so on. The Laplace routines implement stable algorithms and provide high performance on a variety of hardware. So here is the image of the memory hierarchy. So now let's go through memory management. The computer memory hierarchy includes registers, cache, main memory, and disk. Arithmetic and logical operations are performed on the contents of registers, and the other storage units access temporary storage for the data on its way or on from the registers. It's as if whenever you need to store change some data in your attic, you move it first to your desk, then backpack, and then your wallet. Make the correction and then move back through your wallet, backpack, and desk. Finally, store it back in the attic. Give you a small illustration of the memory hierarchy. We'll consider a one-level cache. Although most machines have the hierarchy of cache and units, let's see how information moves between main memory and cache. Suppose that m is equal to 128 and n is equal to 32. And suppose for ease of counting that first elements in each matrix and vector lies in the first elements of some page in the main memory. The matrix elements are stored in order a of 1, comma 1, a of 121, comma a1, a of 1, comma 2, a of 128, comma 2, and in the same way. Cache memory is loaded by block. In this example, this means 8 elements at a time. So in the Saxby implementation in which you successively add 2i, the computer first loads a of 1, comma 1, so on a of 8, comma 1 into one block of the cache, x of 1, so on x of 8 into a second block, and let y of 1, comma y of, so on y of 8 occupies the third block. After x of is added to y, Then we need a a of 9 comma 1, a of 16 comma 1, and y of 9, so on y of 16. This will fill 5 blocks of catchy through, and we only have 4. So we have to write over and whole blocks. After ensuring that any updated values are changed in the main memory, in our case, the old y block and a block disappears from catchy. Moving 5 blocks from main memory, let us do 16 out of our 128 into 32 multiplications. If you work in a high performance compiled language such as Fortran or a C variant, we can use our timings of code fragments to estimate the catchy miss penalty. In interpreted MATLAB or overhead marks, the penalty whenever we time a program through, there are many sources of uncertainty. Other processors are running. Even if you are running on a laptop on which you are only user, the operating system still doesn't make other tasks such as refreshing the screen, updating the clock, and tracking the cursor. Most systems have two timers, one that gives the elapsed time and one that tries to capture the time used for this process alone. There is uncertainty in the timer, so the data you collect are noisy. Most timers give trash unless they are time intervals at that are at least a millisecond. Therefore, the loop your timing should do as many operations as possible, but not so many that interruptions by other activity processes contaminate the elapsed time. The time for arithmetic operations often depends on the values of the operators. Dividing by a power of 2 is usually much faster than dividing by other numbers. For example, the adding 0 is usually faster than other additions. The computer uses pipelining, which occurs on many levels, but the fundamental idea is that the execution of many instructions we give the computer is partially overlapped with the other instructions, so it's difficult to assign a cost of single instruction. Compilers optimize our code. A compiler might recognize, for example, that rate of I isn't changed by our code fragment and thus will remove the statement from the loop. Catchy blocks might be for prefetched programs, often access data in order. So computers might predict that subsequent memory block should be loaded into catchy while you are operating on the current one. So here is the image on arrays and various types. What we have discovered about the time for memory access and floating point operations give us the information we need achieve speeds close to the manufacturer's peak performance claims. We do we doing matrix operations. The next problem challenges used to write a matrix multiplication program to do. Alternative to write our own fast algorithm for basic matrix application operations is to use the ones provided in the basic linear algebra subroutine implementation discussed in the top tools slide bar, as we have discussed in the first third slide. And thank you.